Test. Okay, assalamu alaikum. Welcome to this revision session where I will be revising module number 19, electric current and circuits. My name is Mr. Ahmed Imad. I'm a teacher at Khalifa bin Zayed Secondary School. As a disclaimer, this will not be a thorough revision. We will just briefly go over elements of this unit. Okay, let's begin. Okay, first thing we will note is that charges move because of a potential difference, similar to how water flows when there is a potential difference or a height difference. For example, if we consider a dam, we see that water moves from high potential to low potential. So there must be some sort of potential difference, delta V, in order for water to flow. Similarly, charges flow when there is a potential difference. And what provides this potential difference could be any number of elements. It could be a cell. So this is a cell, symbol for a cell, schematic diagram symbol for a cell. It could be a battery, and this is the symbol for a battery. So what these elements do is they provide a potential difference, a delta V. This delta V causes, in essence, charges to flow. And charges flow from the positive terminal of the battery through the circuit to the negative terminal of the battery. You should remember that the current or the charges which flow from positive through the circuit to negative, this is known as the I, or the conventional current. However, electrons flow from the negative terminal of the battery through the circuit into the positive terminal of the battery. Now, how do we calculate the value of this current? Current equals charge divided by time taken for the charges to flow. So the current is uses the units amps or amperes. Q, the charge, in coulombs, and T in seconds. So we can see that 1 amp is equivalent in value to 1 charge of 1 coulomb of charge flowing every second. Okay. Next, we will explore the conservation of charge. As we can see here on the right, I like to use water as an analogy. Suppose we have a main pipe which flows into this junction, this Y configuration, and water will flow off to these 2 branches, the branch on the bottom and the branch on the top. The water entering into this junction must equal the water exiting out of the junction. This is also true with electricity. So if we have charges flowing into this junction, then the current in equals the current out. So how would I solve such a case? I would start labeling each current. So I would label this, the arrow is pointing into the junction. I would label it as in. This current, the arrow is pointing out, so I'd label it out. And finally, this 10 amp branch, the arrow is pointing out, so I would label it as out. Law of conservation of charge, current in, which is 15, equals current out, which is 5, plus 10. So suppose one of them were unknown. So for example, let's consider that the 10 was unknown in magnitude. However, I knew it was flowing outwards. Then I would apply the law of conservation of charge. 15 minus 5 equals x, which equals 10 amps. Moving on to electrical power. Power is the rate at which work is done. It has the unit watts. It's found using the equation P equals I delta V, where I is the current in amps. Delta V is the potential difference across the element in volts. And the old formula, which we know from previous lessons or previous units, P equals energy in joules divided by time in seconds, still applies. So let's consider this example. It says a 6-volt battery delivers a 6-volt battery. So delta V equals 6 volts, delivers 0.5 amps across an electric motor. I represented the motor as a resistor. In reality, it should be represented with this symbol. However, the math still applies. So the question is, what is the power delivered to the motor? P equals I times delta V, which is 6 times 0.5. And your final answer is in watts. Next, for part B, if the motor runs for 5 minutes, how much electrical energy is delivered? P equals E divided by delta T. We know the value of the power. We know the time. Obviously, here we have to adjust. We have to convert minutes into seconds. So 5 times 60. I multiplied by 60 to convert from minutes to seconds. And so now we know the time. We can find the energy, and the energy is given in joules. Moving on. These are some of the symbols you might come across. Now, how do we measure current and potential difference? There are ways to calculate current and potential difference, and there are ways to measure them. So to measure potential difference, we use a device known as a voltmeter. And voltmeters are always connected in parallel to the device. So say this resistor, I wish to measure the potential difference across it. I would connect the voltmeter 1 point in front, 1 point after, or 1 point before, 1 point after the resistor, and take a branch parallel to my resistor and connect the voltmeter. This is how you correctly connect a voltmeter. And if I wish to measure the current, we say we measure the current through a resistor, then the ammeter, which is symbolized by a circle with a capital A inside, must run the same line as the resistor. So it is in series with the resistor. Now, if we consider a wire, what are the factors which affect the resistance of a wire? There are several factors. They're summarized in this table. We have length, cross-sectional area, temperature, and of course, material. So typically, the longer the wire, the greater the resistance of the wire. The thinner the wire, the greater the resistance. Generally speaking, this is general rule. The hotter the environment, or the hotter the wire gets, the greater the resistance of the wire. And obviously, Finally, resistance is dependent on the material. So for instance, if we look here, the lowest resistance material on this table is silver, meaning it is the best conductor. And from this table, the material with the highest resistance, meaning the worst conductor between the elements or the materials mentioned, is platinum. However, you'll notice that copper is not the best conductor, but it is the material of choice for most wires you might come across. And this is because it's a compromise between conductivity and cost. Silver, although it is a better conductor, it's more expensive, relatively speaking, to copper. Ohm's law. Ohm's law relates an element's resistance to the potential difference across it to the current running through it. R equals delta V divided by I. This is a very important equation where R, the resistance, is, I like to think of the unit ohm as a speed bump because it's a speed bump for charges. It slows down the charges. If we can say that's just an analogy. Delta V is in volts, and the current I is in amps or amperes. Let's solve this example. We have a 30-volt battery connected to a 10 ohm resistor. Find the current. So R equals delta V over I. The resistance is 10 equals a delta V of 30 divided by a current I. Solve accordingly to find the value of I in amps. Now this is a real life resistor. Obviously the colors here, although we don't need to know what these colors represent, but they're an indicator for whoever's working in the lab of the value of the resistance. These are designed to have specific resistances. So each color band has a specific meaning. So it's an indication to the resistance of this particular resistor. Now, why do we use them? We use them for numerous reasons. One of the reasons is to control current, because if we rearrange Ohm's law and make I the subject, then we get I equals delta V over R. So we can see that we can increase the current by either increasing the potential difference or by decreasing the resistance. So the opposite is also true. If we wish to decrease the current for whatever reason, all we have to do is increase the resistance. Again, why is this? Because I is directly proportional to delta V and inversely proportional to R. Here we have a variable resistor. A variable resistor is simply a resistor whose resistance value is not discrete. It's not fixed. It can be adjusted according to the setting of the variable resistor. So this toggle here, we can shift it to the left or to the right to set a desired resistance value. Similarly here, this variable resistor has a scroll. And the symbol for variable resistor is this. So over here we have 3 points at which we can, sorry, let's rename that C. 3 points at which we can set this toggle A, B, and C. So A, if we set the arrow at A, then the current will have to go through the maximum amount or the largest amount of resistive material. So at A, we would have maximum resistance. At B, the current will go through half of the resistive material, and C, it will go through barely any of the resistive material. So at C, we will have the minimum resistance. At A, we'll have the maximum resistance. Series and parallel circuits. So these are the most common circuits you might come across, series and parallel. In a series circuit, the circuit on the left, there's only one path for the current to flow. One of the disadvantages of a series circuit is that if one element, for whatever reason, fails, then the entire circuit will be open and no current will be able to reach any of the other elements. While in a parallel circuit, current has more than one path to flow, meaning if one of the elements fail, this would not stop the current from reaching the other elements. And we will get into the specifics of these two later on. Now, using electrical energy, why do resistors and wires get hot? The reason they get hot is, let's consider this section of a wire. As an electron passes through a wire, the wire is not made of empty space. There are atoms inside. When these electrons, charges, are flowing through the wire, they tend to bump into these atoms, transferring kinetic energy into the atoms. The atoms start to vibrate, and this vibration causes the release of heat. So the wires get hot. And obviously, the power transformed in a resistor in the form of heat is given by this formula. There are another two formulas to find the power being consumed by an electrical element. You can pause to see the two formulae here. P equals the current squared times the resistance, or P equals the potential difference squared divided by the resistance. Power and transmission lines. I will not waste much time on this. If we just very quickly look here, this figure shows how power is transmitted to our homes. So we have power being generated at a power plant, electrical power being generated at a power plant at 12,000 volts. This is just an example. These values vary in real life. And then before it's being sent through the long distance lines, it was stepped up, we say, stepped up to roughly 400,000 volts. And then before finally reaching our homes or entering our towns, it's stepped down to lower values. So the question is, why do we step up the voltage? Very simply, it's because of the following. The power loss in a transmission line equals P loss equals I squared times R. Only. This is the only formula we will be using to calculate the power loss in a transmission line. There are two ways to decrease the power loss, because power loss is bad. We do not want power loss. We want to mitigate power loss or eliminate if possible. It's either by decreasing resistance, and we discussed how we can decrease resistance, or by decreasing current. And the effect of decreasing current is more substantial than the effect of decreasing resistance. Reason being is we have this squared for current. And the way to decrease current is to increase voltage. I'll quickly go through how. Suppose we have this machine with power going in, so P in, and power going out, P out. The power going in equals the power going out. Electrical power, of course, is given by the current. So I in V in equals I out, V out. So I out, which is where power losses take place. Of course, this machine being the transformer, I shall call A. I out equals I in V in divided by V out. So we can see here that I out is inversely proportional to V out. So by increasing the voltage, we can decrease the current. And if we can decrease the current, we can decrease the power loss. Energy in kilowatt hours. It's handy in calculating the cost of electricity. Energy equals power times time. Energy is usually in joules if power is what is given, sorry, in watts, and time in seconds. Alternatively, we can use another unit, which is the kilowatt hour, where power is given in hours. And the cost of electricity, C equals the electrical energy consumption in kilowatt hours times the utility rate, usually given in a money currency value, divided by kilowatt hours. Moving on. Let's go to series and parallel circuits. In series circuits, there's only one path for the current to take. And in series circuits, these are the rules which apply. The current, regardless of where you're looking in the circuit, is the same. The potential difference, the way I like to see it, is that the energy flowing into the circuit equals energy flowing out or being consumed. So delta Vs, S being the source, the battery, equals the potential difference being used, which is the potential difference of each individual resistance. And the equivalent resistance is the mathematical sum of the resistances. Equivalent resistance being being a resistor which we can substitute all the resistors of the original circuit with and end up with the same current, provided we have the same potential difference. The potential divider circuit is a series circuit which distributes the voltage across the resistances corresponding to the value of the resistances. And the formula for the potential divider circuit is given here. Delta Vn in general equals delta Vs times Rn over R equivalent. So if we have, sorry, two resistances, R1 and R2, and if we wish to find delta V2, we multiply the potential difference of the source, being the battery, by the ratio of the resistance in question to the equivalent resistance of the entire circuit. Parallel circuits are slightly different. Each branch will have the same potential difference as the battery. However, the current is distributed. Of course, current takes path of least resistance. So if you, at a glimpse, want to know which branch will have the highest current, look for the branch with the lowest resistance. And to find the equivalent resistance of a parallel circuit, we apply this formula. Kirchhoff rules we have two rules. The loop rule, which is the sum of the potential differences in a loop equals 0, and the junction rule, which is the sum of the currents entering the junction equals the sum of the currents exiting the junction. So over here, if we apply the loop rule, this is a loop in red. We have three loops here, L1, L2, and one which goes all the way around L3. If we look at L1 exclusively, the potential difference going in delta Vs equals the potential difference going out, meaning energy being consumed, which is delta V1 plus delta V2. If I know any two values, I can find the third. As for the junction rule, the current entering into a junction equals the current exiting out of the junction. So let's consider junction A. We have three currents. Current 1 is going in, current 2 is going out, current 3 is going out. So I1 equals I2 plus I3. And finally, applications combined and series is neither a pure series nor a pure parallel circuit. So how do I deal with it? The book explains in this problem-solving strategy sheet. You can pause, take a look. But simply what I will do is I will simplify this circuit into a circuit I can better recognize and deal with. So we have three resistors, RA, RB, RC. I won't go into the specifics on how this is done. However, to simplify this, I see that RC and RB are purely in parallel. So I can simplify them by finding their equivalent resistance. And since they are in parallel, then I will apply RBC equals 1 over RB plus 1 over RC to the power of -1 to get RBC. So this circuit simplifies to this. You have RA here, and you have RBC. Now RA and RBC are in series, so I can simplify and find the R equivalent, which would be RA plus RBC, and so on. Test yourself out by finding these values for this circuit. And in general, we can apply Ohm's law or a variant of Ohm's law, two variants. R equivalent equals delta Vs over Is. And another handy form would be Rn, which equals delta Vn over In, where n is any number resistor I choose. So for Ra, it would be Ra equals delta Va over Ia. Safety devices. There are three safety devices we will look at very quickly. If the current going through a line, let's say we have a fuse over here, and the rating of the fuse is 3 amps. The moment the current of this line exceeds 3 amps, the fuse will melt, opening the circuit. And it's used to protect electrical devices from damage, and indeed potentially us humans from being exposed to a high current. Again, when does a fuse melt? When the current in the line exceeds the rating of the fuse. The flaw, or the limitation, I should say, of the fuse is that once it's melted, we need to physically replace it. Unlike a circuit breaker works exactly the same in that if the line current is greater than the rating or the setting of the fuse, the lines or the circuit will open. However, unlike a fuse, you don't need to physically replace the circuit breaker. All you have to do is operate a switch. So here we have a few circuit breaker connected, and if the current exceeds a certain value, the circuit breaker opens the circuit. All you have to do is is operate this switch, and the circuit closes. Finally, the GFI, the ground fault interrupter. Suppose we have a fellow, he's taking a bath or whatever, and he drops a hair dryer into the bath. Let's see what the ground fault interrupter would do. So here's an electrical outlet, and here's our hair dryer, for example. Now, the current going out, let's suppose, has a value of 0.2 amps. And the current going back in equals 0.2 amps. Now, if this hairdryer were to fall into water, what happens is, since water is a conductor, some of the current will leak into the water and potentially causing danger to the whoever's in the bath. So in this case, the current going back into the socket would equal something lower. So let's say 0.1 amp. What the ground fault interrupter does, it compares the current going out to that going in. If there is a change, like in our example, 0.2 does not equal 0.1, the ground fault interrupter detects this change and opens the circuit. And that's it for the first module. My name was Mr. Ahmed. I hope you benefit from this, and please keep an eye out for the Haykel. All the best to you all. Assalamu alaikum wa rahmatullahi wa barakatuh.